Greetings and welcome. We're starting an entirely new chapter, a new zone today, the blue zone. It's talking about combinatorics and probability is the overarching concepts that we'll be talking about. And combinatorics, just so you guys are aware of, is kind of the math or the science behind counting outcomes of things. And probability is a way to describe the likelihood of an event occurring, right? So combinatorics is kind of how many ways can those events occur, and probability is what's the likelihood that a specific event or outcome would occur. So we're focused on the combinatorics portion of this for starters. And today's lesson, the section we're doing, is about permutations. Permutations. I guess it's going to be related a little bit to this mutation thing. I could see that word being in there a little bit. So permutations. Let me start off with an example. Let's say that me, Mr. Waddy, let's say I own 2 pairs of pants. Oh, there's a loop-de-two right there. Let's say I own 3 shirts. And let's say I have like 2 ties. And assuming I have no care about whether or not what I'm wearing matches, I just randomly wake up in the morning and I just like go to my closet and just like grab in the dark. Like I know where the pants are, so I'm not going to accidentally try to wear like a shirt as a pair of pants. Like I know I'm getting one of each of these things. All right, and I want to figure out how many different, I don't know, do adults call them outfits? What do they call it? I don't know. Outfit, I don't know. Okay, all right, sure. And I think it was actually, oh man, there's a definite loop-de-two and a Z2 right there, 2Z. I think Albert Einstein supposedly stopped wearing different types of clothes. He just wore the same kind of outfit. He had duplicate shirts, duplicate pants, because he felt it was a waste of his brain time to figure out what he's wearing every day. So one of the ways I could figure this out is let's talk about pants. So here's my starting decision. I've got 2 choices. Actually, let me make it a little bit broader. So I could choose pants 1 or pants 2. All right. So I've got to start by making some decision here, right? So let's do that. So I choose 1 pair of pants. The next thing I got to do is I got to pick a shirt. And whichever pair of pants I chose, it's not going to change which shirt I wear. So for each of these cases, I have 3 options. Let's see, maybe like that. So I could have shirt 1, shirt 2, shirt 3 for each of those outcomes. And then I have to pick my tie. And I've got 2 ties to pick from, and assuming that whatever pair of pants and shirt I chose will not affect which tie I'm wearing, all right, there's 2 ties to choose in each of these possible timelines or paths. So I could have T1, T2, T1, T2, T1, and kind of like Back to the Future with multiple timelines and parallel universes, and some Mr. Waddy in some universe happened to choose pants 2, shirt 1, and tie 2, right? Whereas maybe another one didn't. I can now actually figure out, looking at this is called a tree diagram, because the way kind of it branches, where I can actually now just count how many outcomes there were. So for instance, this little dead end leaf here or whatever was pants 1, shirt 3, tie 1, right? Or this one here was pants 2, shirt 2, tie 2, 2, 2, 2, bam, right? So the total number of outcomes appears to be 12. 12 ways that this could have happened, right? Assuming I, as an individual, do not care whether or not I match in any capacity, right? Now, it turns out that because these events, the way I've described this scenario, are independent of one another. They had no effect on the other. For instance, I didn't say, okay, if I choose my black pants, then I only have 2 shirts to choose from that would match those, right? I just described it doesn't matter, right? You have 3 choices for shirts, no matter which pair of pants you chose, right? These are called independent events. And what I can do to calculate this a little bit easier is, as long as this is independent, I could have figured this out by multiplying the number of pants I could have chosen, right? The number of outcomes I had there, the number of shirts, and the number of ties. And that also is equal to 12. All right, and that is due to the independent nature of these choices, at least in the way I described them. So this is a tree diagram, and then this is this concept right here we're going to expand upon in a little bit. But let's first talk about what I mean by independent events. Or actually, let's ask, what do you guys think independent events are? Or maybe you could give me an example of what you think 2 independent events would be. So any events that don't change each other or don't affect each other. Yes, bless you. Bless you. All right. That one event's outcome will not change or affect the possible outcomes of the second event. So for instance, like examples of that would be flipping 2 coins. Right, that whatever I get, like just because I get a heads on the first one does not change the probability of the second coin's outcome, right? It's still going to be the same, right? Let's talk about dependent events, which I'm guessing you guys could probably describe. Yeah, any events that are directly related to one another. Have a direct effect on each other. So that could be like maybe drawing 2 cards from the same deck. Right? That I can't draw a 3 of diamonds and then also draw another 3 of diamonds because it changed the possible selection the second time I drew, right? It was a different number of possible outcomes that were available to me because of my first decision, right? Or if back to my getting dressed in the morning problem, if I said, okay, if I choose black pants, I can only pick from these shirts. If I chose brown pants, I can only pick from these shirts, right? Where those events are suddenly having an effect on one another. Now, I'm going to tell just kind of a little quirky, somewhat morbid story that when my brother was in college, this is what his probability statistics professor told him about. So you don't have to write this down. I'm just going to draw a picture. So suppose, so this professor said, oh, I go flying on an airplane, right? And so here's this airplane that he goes flying on. Oh man, that tail got really sad real fast. I don't know, something like that. Yeah, so he goes flying on an airplane, right? And he's all like, so when I go flying, I'm afraid of flying. He's like, I'm terrified. And he, say, happens to know the probability that a bomb is on the plane. Okay, he's like done his statistical analysis, and he's all like really scared about bombs, right? He's like, this is terrifying. And he happened to find out that the probability of a bomb on the plane, let's say, is 1 in 10 to the ninth, or something like that. All right? So I think that's a billion, if I did that right. Right. 1 in 1, 2, 3, 4, 5, 6, 7, 8, 9 billion. All right? Let's say that's the case. I think the probability is actually far less likely than that. Right? So he's like, okay, man, that's terrifying, right? And he ends up thinking, he's like, well, what I'm going to do is I'm going to bring my own bomb on the plane. And the reason is, what's the probability of 2 bombs being on the same plane? Right? Because that would be like 1 in 10 to the 9th times 1 in 10 to the 9th, which is like 1 in 10 to the 18th. He's like, so I'd be super safe, right? Because I'm not going to detonate my bomb on the plane. I'm just bringing it there for safety reasons, right? But what's the problem with the logic of his story? Well, there is still a bomb on the plane, okay. Not to mention the fact that he probably wouldn't get on the plane and he'd be thrown in prison, right? He's like, no, this isn't a terrorism bomb. This is just like a safety bomb. It's an anti-terrorism bomb. It's here to reduce the likelihood of another bomb that was intended for harm, right? Well, part of the reason is, yeah, in general, these 2 events would have been independent, right? It would be really awkward, like, if a terrorist stands up on the plane and is like, all right, everyone, I'm taking this plane hostage. But then at the same time, another terrorist, just like 1 row over, stood up and did the same thing. And then they like kind of look at each other and is like, oh, you were taking the plane? I was going to take the plane hostage today. What? Oh, this is awkward. So you want to flip a coin on this? Like, how do we decide who's doing their thing today? Who are you going to kill these people for? Oh, I was going to kill them for this reason. It'd be really awkward, right? That would be this situation. How likely it is that, 2 completely independent groups of terrorists happen to make that same decision the same day. Once again, like I said, this is a little bit morbid, perhaps. However, in the case of the professor, he does not have a 1 out of 10 to the 9th power, a 1 in a billionth likelihood of his bomb being on the plane. His bomb being on the plane is a certainty because he made it that way, right? So he's not applying the probability, right? His bomb is a guaranteed outcome, right? He's kind of working the system against it. He chose to put that bomb on the plane, not the other way around. So I can't say his bomb being on the plane was a 1 in 10 to the 9th because from his perspective, he forced it to be there. So he's actually not changing the outcome at all of the other bomb being there, sadly. So kind of an interesting concept, but it has to do with independent events, right? If they were truly independent, then yes. But the fact that he was manipulating the situation is what messed it up. That's unfortunate. So let's see. So we've talked about independent, dependent. Let's talk about the basic counting principle. Basic counting principle. Nope. L-E. Man, there we go. That's all right. I'm a math teacher. I'm allowed to spell things wrong. So the basic counting principle is regarding different events. So let's see. Suppose one event can be chosen. This is going to be a lot of writing, so if you're watching this on YouTube, feel free to fast forward. It's quite a bit of alliteration there. Suppose one event can be chosen in P ways. P different ways. Right, P many ways. Like my pants. I had 2 pairs of pants to choose from, or 3 shirts. And another event, another independent event, can be chosen in Q different ways. Okay? Then the two outcomes can be chosen successively.